Yes, sir.
Today I am giving a talk on instruments and methods used in the environmental radioactivity studies. We are all familiar with different types of radiation. We classify these radiations based on the energy into ionizing radiations and non-ionizing radiations. Ionizing radiations are the one which have the ability to ionize atoms and molecules. That means they will have a minimum amount of energy, say 32 electron volts. Non-ionizing radiations are those which have very low energy and they cannot ionize the atoms and molecules. Mobile radiations, radio waves, TV signals, these are all examples for non-ionizing electromagnetic radiations. Ionizing radiations, examples may be electrons, alpha particles, gamma radiations, beta particles, and many radiations which are emitted in the cosmic rays. In the ionizing radiations, we can understand them into two categories, in two groups. One type of particles which directly ionize the matter, and other type of particles which indirectly ionize the matter. Directly ionizing particles are charged particles, electrons, protons, etc. Indirectly ionizing particles are neutral particles like neutrons, gamma ray, photon. They don't have charge, but they will transmit the energy by which electron is ejected out of the atom. These radiations are originated from natural sources and also through man-made sources. We are all exposed to the radiations from natural and also man-made sources. We call this exposure as irradiation when the radiations are emitted from the outside the body, like gamma radiations irradiating on our body. And also through external contamination when we are handling the materials which contains trace amounts of radioactive elements. The third way of radiation exposure is through internal contamination. Contamination through food and through inhalation. We drink water. Water may contain trace amounts of radioactive elements. We inhale and exhale air. Air may contain radioactive elements. Uranium is one of the primordial radioactive elements present in nature. There are three primordial radioactive series: uranium-238, uranium-235, and thorium-232. These are present from the time of origin of the universe. Uranium will undergo radioactive decay, series of radioactive decay. Its half-life, you can see, it is 10 to the power of 9 years. It is almost equal to the age of the Earth. Uranium will undergo radioactive decay and produce radium. I have named only the elements which are of interest to us. Radium is another important radioactive element contributing significant radiation to the population. Its half-life is 1600 years. It will also undergo radioactive decay by emitting alpha particle of 4.6 MeV and 4.8 MeV energy. Radium will decay into radon-222. Its half-life is 3.8 days. It's a noble gas. It will also undergo decay by emitting alpha particle of 5.5 MeV. Being a gas, it can enter into the atmosphere and produce many radioactive elements by radioactive decay. Polonium-218, lead-214, bismuth-214, polonium-214, lead-210 are the decay products of radon. These are all very active solid particles present in the natural environment. They will undergo radioactive decay through alpha, beta radiation, and also they will emit gamma radiation. That means they will cause significant health risk to human beings. These we classify into short-lived and long-lived decay products. Short-lived decay products are hazardous to health because of their high activity. These two are other two decay schemes of primordial radionuclide, uranium-235 and thorium-232. You can see similarity between all the three primordial radioactive decay series. The first decay series has got radium isotope radium-226, second one radium-223, and another one radium-224. Radon, in the uranium-238 series, its mass number was radon-222. In the uranium-235 series, its mass number is radon-219. In the thorium decay series, its mass number is radon-220. Mass number is 220. The half-life of radon-219 is 4 seconds, and half-life of radon-220 is 56 seconds. Because of the short half-life of this element, radon-219, this can be normally ignored because before entering into the atmosphere, this element undergo radioactive decay and it cannot come into the atmosphere. Even if you find it will be very, very small quantity. This one, radon-220, half-life is also small. It is less than a minute. But because of higher concentration in some type of soils, particularly in South India, we can see significant amount of radon-220 in the natural environment. That means the abundance of thorium-232 is more. Because of the higher abundance, we can found trace amounts of radon-220 in the atmosphere. Whereas the radon-222 half-life is 3.82 days. That means there is a possibility of entering into the atmosphere before it will completely undergo radioactive decay. Similarly, similar to the first series, this radon will undergo radioactive decay in the atmosphere and produce so many other radioactive elements. Radon atoms will enter into our atmosphere through the pore spaces present in the Earth crust. They will then transported to the environment through diffusion, convection, and advection. Diffusion is a process in which the particles will move from higher concentration to lower concentration. Similarly, because of the temperature gradient, the particles will move. We call it as convection. That means the temperature of the surface of the soil will vary throughout the day. During night time, it's cool. Surface of the soil is cool. During daytime, because of the solar heating, the surface of the soil is hot. This will create a temperature difference between the different layers of the soil. This will set up a convective motion for the radon gas particles. That means higher temperature to lower temperature, the particles will move. That means particularly during night time, the soil layers which are at deeper depths, they are warmer compared to the surface soil. That will allow radon to move because of the convective motion from the earth crust to the surface of the soil. There is other process, advection, that is because of the pressure variations. From higher pressure to lower pressure, the concentration, the radon particles will move. The amount of radon that escapes to the atmosphere depends upon several parameters. We can identify these. That means the amount of radium in the ground, the type of soil cover, whether it has a porosity, moisture, and its temperature, atmospheric temperature, that means properties of the atmosphere, its pressure, and other meteorological parameters. Among the natural background radiation, the radiations can be classified or quantitatively measured, and we can have this type of variation. About 55% of the radiation dose received by the public is because of the radon alone. Whereas cosmic rays contribute about 8% of the total radiation dose received by the public. Cosmic radiations. Terrestrial radiations, that is terrestrial gamma radiations, will contribute 8%. Internal radiation will contribute 11%. Internal means we consume food. Food contains radioactive elements like radium will be there, uranium will be there, radon may be dissolved, and also potassium isotope K40 will be there in the food and water. Medical X-ray exposure is contributing 11%. Nowadays, occasionally, people are at least once in a lifetime they will take X-rays. It will contribute. X-ray photography will contribute about 11% of the total radiation dose. Nuclear medicine, consumer products, and others maybe of a special type, flight travel or travel in the spacecrafts, underground mining. All these things will contribute about less than 1%. That means from that chart we can identify that radon is the major contributor to the radiation dose received by the public. This gas is discovered by F.E. Dar in 1900s. And that means that during the birth of nuclear physics only we can identify. It was named Niton in 1908 by Ramsay and Gray because of its luminosity. It was identified. It was luminous because it will emit the alpha particles. It looks like light radiations, flash of light coming out of the radon gas. Other isotope of radon, the thorium emanation, was discovered by Ernest Rutherford in 1900. Debrine and Giesel are credited to the discovery of the other isotope, third isotopes, actinium. Please, all the participants, mute your.
Pratibha, please mute yourself.
Regarding the properties of radon, it is a colorless, odorless radioactive gas. In the normal atmospheric condition, it is you will find physically gaseous form. It will undergo radioactive decay through alpha by emitting alpha particles. These properties help us for the detection of the radon gas. There are three isotopes as I shown in the decay schemes: radon 222, radon 220, and radon 219. Their half-life is also shown in this table. How radon is emitted from the soil grain? This can be qualitatively understood by this diagram. Radon is emitted, it will gain initial kinetic energy by recoil velocity. When radium emits alpha particle, radium becomes radon. Alpha particle is emitted in one direction. In the opposite direction, a radon atom will recoil. Radon will recoil in the opposite direction. This recoil velocity is very small because of its useless conservation of the momentum. If you think, recoil velocity is very small. In this diagram, say because of its recoil velocity, it cannot small recoil velocity. It cannot penetrate in the soil grain for a longer distance. It can move only a small distance. In this diagram, see this arrow mark. If this is the position of the radium undergoing radioactive decay, and alpha particle is emitted inwards, that means towards the center of this soil grain, then radon is pushed outside the soil grain. But there is a possibility of another soil grain, therefore, presence of another soil grain, and this radon may be trapped in the second soil particle. That means from this soil particle, radon will go to the second soil particle, and it cannot come out of this soil particle. It will. Other possibility, if you think, if the alpha particle emission is outside the soil grain, towards outside the soil grain, then radon will go towards the center of the soil grain. In this case, also it cannot come out. You see this diagram. In this case, it is entering towards the pore space, and if pore space is filled with water molecule, that will also affect. And that will sometimes water molecule will help the radon atom to come out of the ground into the atmosphere. And sometimes if this radon molecule enters this pore space, it will diffuse into the atmosphere through the pore space. That means we'll get the radon. We'll find the radon concentration in the atmosphere only if it forms on the surface of the soil, and if its emission is towards the pore space. Otherwise, we'll lose the particle. That means several factors will affect the concentration of radon in the atmosphere. In this study, we must familiarize with a few radioactive units. One is gray. This is the unit of observed dose. 1 gray corresponds to the deposition of 1 joule of energy in 1 kg of material. This unit is familiar with most of us. Sievert is the unit of equivalent dose. It is the product of observed dose in gray and the radiation weighting factor. That means it is also 1 joule of energy absorption in 1 kg material. But in this case, in the equivalent dose, this material will be the biological tissues. Therefore, the weighting factor we have to consider, because each tissue has got different sensitivity to the radiation. Say skin may be less sensitive to the internal tissues. That means each tissue has got its own weighting factor. We have to multiply the observed dose with the weighting factor, we will get the sievert. Usually, these quantities are expressed in sievert. When we want to estimate the inhalation dose, injection dose to the population, we express it in sievert. Working level is another unit which is especially used for radon daughter products. It is a combination of radon progeny such that the total alpha energy released in 1 liter of air is equal to 1.3 10 to the power of 5 MeVs, because radon progenies are having different energies and different half-lives. Combining all the progenies, there are so many progenies in the 3 radioactive decay series. A working level unit is defined in this way. That means it is a combination, any combination of radon progeny, so that total energy is 1.3 into 10 to the power of 5 MeV. And radiation weighting factor also we have to consider. For photons and electrons and mesons, radiation weighting factor is 1. For neutrons of low energy, it is 5. For neutrons of energy from 100 keV to more than 100 keV and less than 2.2 MeV, it is 10. Like that, for different particles, we have different weighting factor. Now, with this background, I am coming to the instruments which are used in the environmental radioactivity. In this field of research, we first take this surveymeter. This is scintillation surveymeter, used to get a broader picture or a crude picture about the presence of radioactive elements in the environment. The first thing is to measure the background gamma radiation. For this, we have to use scintillation-based gamma ray surveymeter. GM counter-based surveymeters are also available, but this will give you good results. That means this will give an idea whether this environment contains really high background radiations and also the radioactive elements. Possibility of getting the radioactive elements in the Earth surface. Now, I am going to describe about the few equipments which were used earlier and not presently known is using these equipments. This is the low-level radon detection system. Low-level radon detection system. This is developed at a BARC by a group of scientists. This is, as the name indicates, this instrument can measure the very low levels of concentrations of radon, say 4 to 10 becquerel per meter cube. That means in 1 meter cube of air, if the activity is 10 alpha particles are emitted in 1 meter cube of air, that amount can be measured with this radon, with this system, LLRDS system. This is a cylindrical metallic chamber. I am describing this instrument because all the modern equipments are somewhat based on the principle used in these old equipments. This is a cylindrical chamber made of aluminum. That is a conducting material, lightweight conducting material. This will be pre-evacuated before going to the sampling location. You will evacuate this cylinder. At the sampling location, there is a opening which is connected to the swage lock. That means when we press this, it will open this chamber, and immediately if you remove, it will automatically close this chamber. That means at the location, we'll open this chamber, and sampling air will be filled inside this chamber. This volume is about 5 liters. In the laboratory, will apply a potential to the lid. This lid, bottom of this lid has got a metallic plate. Bottom of this lid has got metallic plate. To that metallic plate, the potential is applied. Negative potential of 800 volts is applied. Inside this chamber, radon concentration will be there. Radon atoms will be there. They will undergo radioactive decay. They will produce, they will emit alpha particles, and you will get radon progenies, polonium. After some time, you will get lead. After some time, you will get bismuth, like that, because all of them will have very small half-lives. That means this gas now in the laboratory contains radon progenies, lead, polonium, and bismuth. It is known that all these progenies are charged particles. Unlike noble gas radon, these particles are charged particles. They are very active. And it is also known that they are all positively charged particles. All of them are positively charged particles. Because of the electrostatic attraction, these particles will accumulate on the metallic plate. All the particles, radon progeny, mainly the polonium atoms, will accumulate on this metallic plate. After 1.5 hours of charging, we'll remove this plate, and this is fed to the alpha counting system. That means we'll count the number of alpha particles emitted by a polonium element which is physically sitting on the metallic plate. That means radon was there inside this gas. It has emitted polonium. These poloniums are charged particles, and these charged particles are sitting on this metallic plate. This plate will remove and count for alpha activity. That means alpha counting system will measure the alpha particles emitted by the metallic plate. That means indirectly we get the concentration of polonium which is on the metallic plate. From this formula, by knowing the radioactivity loss, and also by counting, knowing or measuring the counting delay, and taking all other parameters into consideration, finally we'll get the concentration of radon in the environment using this formula. C is the counts, and the 1000 is the conversion factor from liter to meter cube. V is the volume, E is the efficiency of the counting system, F is the factor given by this formula. It depends upon the relative humidity. Z is the theoretical correction formula. Similarly, for the measurement of radon progeny, we can use this type of instruments. This is called as the airflow meter. Airflow meter. Nowadays, we have modern electronic devices, but basic principle behind these equipments remain the same. In this airflow meter, there is a filter paper. We will fix a filter paper here. Air is sucked through the filter paper. That means other end of this pipe is connected to the filter paper. This is a perspex material. There is a cylindrical hole present inside this at the axis of this perspex material. That means air will pass through this filter paper and move in this direction, and finally it will go out of the vacuum pump. On this filter paper, all dust particles along with radon progenies are collected. We select the filter paper pore size of 0.8 microns, so that because all the particles are bigger than this size, and flow rate of the air flow rate can be monitored here. We will keep a specific level, say 40 liter per minute, as the standard flow rate throughout the experiment. We will remove the filter paper, and this filter paper is counted for alpha activity using a alpha counting system. There are so many methods. This is the best method by which we can get the concentration of all the three isotopes: lead, polonium, and bismuth. Historically, we know polonium. We identified polonium as radium A, bismuth, and lead as radium B and C particles. Because these three isotopes have got different half-lives, and they are undergoing successive radioactive decay. Decay logs, successive radioactive decay log is very well known to all of us. That means radon will decay into radium A will decay into radium B will decay into radium C. That means radium B will undergo radioactive decay, and also it will form. Its number will increase and also decrease. Increase because of the radioactive decay of radium A, and decrease because of its own radioactivity. Similarly, there is a formation of radium C and also decay of radium C. And we have a set of equations where C1, C2, C3 are the counts noted during 0 to 4 minutes, 5 to 15 minutes, and 15 to 30 minutes, like that. During 3 intervals of time, the progeny alpha particle can be counted, and that information can be used to get the concentration of individual radioactive elements, radium A, B, and C. By knowing the concentration of radon and its progeny concentrations, the radiation dose, inhalation dose to the public can be calculated using this standard formula, where this is the concentration of radon and the FR is the equivalent factor. For the interest of atmospheric physicists, the ion pair production rate can also be calculated by knowing the concentrations of radon and its progeny. This is the formula. Total energy due to radon and its progeny is given by 5.49 MeV into concentration of radon, 6 MeV into concentration of radium A, 0.85 MeV into concentration of radium B, 7.69 MeV into concentration of radium C prime. I have marked C prime because it's alpha emitting particle. C is not an alpha emitting particle. It is a beta. It will undergo beta decay, but its half-life is very small, short-lived element. Therefore, they both are in equilibrium. That means radium C prime concentration is equal to radium C concentration. This is the total energy of the radon and its progeny. This is the number of ion pairs created, number of ionization done by these elements. That means energy divided by 32 electron volts per ion pair. We can measure how much radon is emitted from the ground surface. This parameter is known as the radon exhalation rate. Quantitatively, we can do it. This is the experimental setup to measure the radon exhalation rate from the ground surface. Earlier equipment is for the measurement of radon and its progeny in the environment. This is the equipment to know how much is being emitted from the ground surface, and also a similar setup can be used to find out the radon exhalation rate from the walls and floors of the buildings. A part of the cylinder is buried inside the soil, and a part is in the atmosphere. Radon exhaled accumulated in this chamber, and we use a rubber bulb to mix the air before collecting. This other opening can be connected to the radon counting system. And I have written is LLRDS, but any other radon counting system can be connected to this opening, and the amount of radon collected after say 30 minutes or 15 minutes is measured, and from that way we can find out the rate of exhalation, radon exhalation from the ground surface. This is the formula used to quantify that parameter. Now I will describe about an important device used in the environmental radioactivity. Many times we want to do a large number of measurements simultaneously. Say at 500 houses, we want to measure the radon concentration. If you want to measure at 500 houses, we cannot have 500 low-level radon detection systems. It is highly impossible. But measurement is very important and it is needed. In those cases, low-cost devices were designed and fabricated. This is one such instrument used throughout the world for the measurement of indoor radon and its progeny concentration. This instrument, which is shown in this figure, is designed and developed in the Baba Atomic Research Center. Similar instruments have been used throughout the world. This is we call as a pin cup dosimeter. That means this instrument has got two chamber. This is one chamber and this is another chamber. Separating the two chambers, there is a wall made of same material. This in this picture you can see. That means in between there is a wall, and in these chambers we fix the material which is sensitive to alpha particles. This is the nuclear track detector. We call it as a solid state nuclear track detector. And this is a very familiar detector, and also its cost is negligibly small, but not negligible, so it's a low cost element. This is manufactured by Kodak company. Its name is, code is LR115. LR115 is the name of this film. The properties of these films are interesting. This is sensitive only to the alpha particles. It is not sensitive to beta particles and gamma radiations. That means only alpha particles can cause tracks, visible tracks in the film. Only alpha particles can cause tracks in this film. Beta radiations and gamma radiations, they don't cause the tracks, visible or significant tracks. And also this is not sensitive to the light, that means ambient light, and also it is insensitive to moisture content and variations in small variations in temperature, etc. That means it is this film is suitable for the study of radon concentration in the environment. As I was telling about the two chambers, in the chamber 1 we fix a film, SSND film. In the chamber 2 also we fix the SSND film. But this chamber is covered with a filter paper. A glass fiber filter paper is put in this chamber. It is shown here. Filter paper is put. In the other chamber, we will fix a filter paper and a membrane sheet. Third film is also fixed. It is on the surface of this cup. On this surface of the cup, a third film is fixed. It is not covered by anything. In this chamber, it is fixed with only the filter paper. Into this chamber, radon-222 isotope can diffuse. Radon-222 isotope can enter into this chamber. And also radon-220 isotopes can also enter into this chamber. These are two gases. Whereas for the other chamber, only radon will enter and radon-220 is avoided. It is attenuated because of its half-life. It is attenuated. That means in this chamber, only radon will enter. In this chamber, both radon and thoron will enter. We call radon-222 as radon-220 as thoron because it is emitted by the thorium decay series. We are not interested in the actinon, radon-219 isotope, because its concentration is small and also its parent concentration is also small. Actinium concentration in the earth is small. It is negligible. Okay, that means in this chamber, radon will enter and also thoron will enter. It will undergo decay by emitting alpha particle. These alpha particles are the alpha particles can form tracks in this film. It will make a hole If a particle falls in this direction, emits in this direction, it will make a hole. That means not alpha particles will make holes on this film. Only alpha particles which are emitted from certain distance inside this chamber, in this direction, they will cause tracks in this film. Similarly, in this chamber also, on this film, alpha particles emitted by radon, thoron, actinon, and all its their progenies will make tracks on this film. That means here we'll find more number of tracks, that we say 400 tracks per centimeter square. Here we'll say 300 tracks per centimeter square. Here in this chamber we may find 100 tracks per centimeter square, like that. This is the schematic diagram. These tracks produced, they are of the size very small. They are of the size of atomic level, 1 angstrom, say 1 angstrom, 10 to the power of minus 10 meter. These tracks are not visible to naked eyes, even to the microscope or to any equipment. Therefore, this track's size should be enlarged. Track size should be enlarged. It should be made into bigger size. And also, the tracks produced by the alpha particles, they are not throw holes. It is produced at the surface at some point in the conical shape. If you are interested in the shape of the track produced by the alpha particles. Therefore, throw holes must be formed for clear visibility. That can be done through a chemical etching process. That means these films are immersed in a etching bath inside the sodium hydroxide solution at 60 degrees Celsius for 1 hour. For normal, that means 10% sodium hydroxide solution is used to etch the LR115 films. And that means after etching, these tracks can be seen through microscope. And track density can be calculated. Track density means number of tracks produced per centimeter square can be counted. But this counting process is a difficult process if you want to do through microscope. Therefore, a special device called spark counter has been fabricated at a BRC. They have designed this equipment to count the track density of the LR115 films. So this using this device, we can calculate we can count the number of tracks produced by the films. That means this equipment is required because we are doing in a large quantity. Say at a time we want to count at least 100 films, then that will help. By using the track counts in 3 chambers, using the formulas developed, we can calculate the concentration of radon, thoron, radon progeny, and thoron progeny. Now, nowadays, there is a development in the design of this twin cup chamber. Now, they are, instead of using the films, membrane film, and the filter paper to cover these 2 chambers, instead of these 2 items, now they have formed small pinholes. Those dosimeter cups we call as pinhole dosimeter cups, because the properties of the filter paper and mylar film was not uniform. If you are getting from different companies, and also for a usage for a longer period of time. To avoid all these drawbacks, now pinhole dosimeters have been developed and are now being used throughout the country. And these dosimeter cups, they are fixed in a house for a period of 3 months. Therefore, it will give an average value of radon concentration for a period of 3 months. Using 3 months, if you repeat the experiment over a year, 4 times a year, that means covering the winter season, rainy season, summer season, autumn season, we can find out in which season the concentration is more, in which season it is less, or in which period of time it is high or low. That can be used to quantify the radiation dose. Now for the estimation of radioactive elements itself, like radium, thorium and potassium, in the soil samples and rock samples, HP detector has to be used. HP detector is used because of its good resolving power and also relatively good efficiency. In some of the laboratories, people use sodium iodide activated with thallium crystal detector, but in that case, the crystal should be of good quality and bigger size, at least 3" by 3" crystal sodium detector. If you use, we can count the activity of radium, thorium, and potassium elements in the soil samples and in the rock samples. But if we use a HP detector, we'll get the good result. But the counting will be for a longer time, because the activity from the natural sources is very, very small. And even for that means, because it's very small, it should be shielded properly with the lead, with lead shielding, and also counting duration will be for a long period. It means say 7 hours, 10 hours, etc. We have to count. By knowing the concentration of radium, thorium, potassium, observed dose, and several other parameters can be calculated. In liquid samples, we can measure uranium, radium, and radon using different instruments and different techniques. Uranium can only be measured using a laser fluorimeter and also LED fluorimeter. Nowadays, people are using LED fluorimeter. This is in India. It is manufactured by Quanta Laser company. They were earlier making laser fluorimeter, and after that, nowadays they are selling the LED fluorimeter. This is the sole manufacturer. This company is the sole manufacturer of these devices in our country. It will cost about 10 lakh rupees. Using this device, we can get the concentration of uranium in all types of clear liquid samples. That means in water, and if you dissolve any organic material or other material in suitable solvent, you can get the concentration of uranium in those materials. Radon concentration can be used using radon bubblers. This is the schematic diagram and the actual photographs of radon bubblers used for the radon studies. Left side is the schematic diagram. This radon bubbler is made of glass tubes. In this tube, main tube, water sample is filled. We can collect. I'll show another film. Right? This is called as Lucas cell. This is the actual photograph of the Lucas cell. This Lucas cell internal area is coated with zinc sulfate. We know the properties of alpha. Alpha particles are observed even by a thin sheet of paper. Therefore, constructing a detector for alpha particles is very difficult. That means we cannot measure with a GM counter or sodium detector or any other conventional counters which are available in most of our laboratories. Therefore, for alpha particle detection through scintillation method, if we want, we will use zinc sulfate as a scintillating material. Zinc sulfate activated with silver. This is coated in the powder form to the inner walls of the Lucas cell. Lucas cell. This is the Lucas cell. Outer surface is looking painted with black color. The inner side is coated with zinc sulfate. This Lucas cell is evacuated before sampling. It is evacuated. We will evacuate the Lucas cell, and this is connected to the bubbler. Here I will connect the Lucas cell. Okay, this Lucas cell is evacuated. Therefore, air will pass in this direction, and it will enter into Luca cell. Okay, that means air will enter into this Luca cell through bubbling the water which is filled in the bubbler. A filter paper is suitably connected so that it creates small bubbles. That means instead of getting a larger bubble or immediately transferring the air, it will be in the bubble form. That means radon dissolved in this liquid is carried through the air bubbles and it will enter into this Luca cell. That means now this Luca cell contains radon which was dissolved earlier in water samples. And now it will undergo radioactive decay. Radon will undergo radioactive decay by emitting alpha particles. And after the decay, these alpha particles will hit the surface of the inner walls, which is coated with zinc sulfate scintillation material. That means with this interaction, we will get a flash of light. A light scintillation is emitted from the detection material. This flash of light will be transported through optical coupling through this glass window. That means, as shown in this figure, this Luca cell contains radon concentration. Radon concentration will emit alpha particles. These alpha particles will cause light scintillations. These light scintillations are transported to the photocathode of the PM tube. In the PM tube, you will get the electrical pulses that will be counted using a programmable counting system. That means radon concentration in water can be measured in that way. When we come to radium, the concentration of radium in water is very, very small. It's very, very small. And also because of its longer half-life, its activity is also very small. Radon activity is large because of its short half-life. Its half-life is 3.42 days. That means if 10 particles are there, 5 particles will decay in about 4 days. Whereas 10 particle radium is there, 5 particles will decay in 1,600 years. The radium half-life is very large. Its half-life is 1,600 years. That means we need 1,600 years to reduce to its half of its original number. Therefore, its activity is very small and to detect by the alpha counting systems. To overcome that, what we have to do is we have to collect a large quantity of water sample, say 20 liters. We will collect 20 liters of water sample and we pre-concentrate this water sample by chemical method without losing any radium atom in the water sample. That means we put magnesium oxide, and this magnesium oxide will precipitate all the metal elements and also the radium. That means precipitation will occur. We can remove the top surface of the soil, and also by by increasing temperature of water, it will be slowly evaporated. Water will be slowly evaporated. We will heat it at 60 degrees Celsius overnight. Slowly we will evaporate water sample. A concentrated water which contains the whole radium which was originally present in 20 liters of water will be taken, and this water will be filled into these bubblers. I will go to the previous slide. That means 20 liter of natural water sample will be reduced to 60 ml. This is a very tedious process. It will take 5-6 days total time. That means 20 liter is reduced to 60 ml and filled inside this bubbler. This radium will undergo radioactive decay producing radon. Radon and radium will reach equilibrium after 3-4 half-lives of radon. That means half-life of radon is 4 days, about 4 days. If we keep it for say 20 days, the radon activity will be equivalent to the activity of radium. We'll call them as transient equilibrium. Both are in transient equilibrium. That means the activity of radium can be obtained by measuring the radon concentration. After keeping it for 21 days, we'll measure the radon concentration in these bubblers, and from that, by using these formulas, radium concentration in water can be measured. This is the formula. This is the counts, volume, efficiency. These are different times. Those times are given. That means it depends upon the time of collection, time of counting, and also time of storage to keep to achieve the equilibrium between the two elements. Using this formula, one can find the concentration of radium. It will come in millibecquerel per liter, whereas radon concentration will appear in becquerel per liter. All these measurements can also done using another device called as smart radon monitor. Smart radon monitor. I shown an exhalation chamber. Similar thing can be connected to this chamber. This equipment is also developed by Baba Atomic Research Center, and this is exactly similar to all my previous equipments. Principle remain the same, but it's a sophisticated device, and our tedious processes have been totally reduced. Directly, you can put the soil sample into this chamber and get the exhalation rate. This is the scintillation detector. Same Lucas cell is fixed here. This Lucas cell is fixed here in this chamber. This is the actual photograph. This has got so many advantages. This can be used to measure the radon in water also. Radon in water, radium in water, radon exhalation rate, radon concentration in air. Everything can be done using this smart radon monitor. Internationally, AlphaGuard and RAD7 are the equipments used to do these type of measurements. AlphaGuard and smart radon monitors can be compared for their working efficiency and other parameters. But cost-wise, its cost is very small and affordable by colleges and universities. And whereas AlphaGuard will cost about 30 to 40 lakhs rupees, this will comes below about 5 lakhs rupees, along with all accessories to measure radon in air, water, and also exhalation rates. Using these formulas, we can measure the concentrations. Okay, I think I have another 20 minutes time. I'll continue with this. These radioactive elements, they not only affect our health, they are also affecting the atmosphere by charging the particles. That means in the environment, they will create positive and negative ions. Say, radon will emit 5.5 MeV alpha particle. Radon will emit 5.5 MeV alpha particles. For creating one ion pair, we require only 32 electron volts. The energy of alpha particles is in million electron volts. That means million number of ion pairs, positive ions and negative ions, are created by radon and its progeny. Through this process, it will create positive ion and an electron, and this electron, if it attaches to a neutral molecule, it becomes a negative ion. It will surround itself by so many neutral ions, and it will become a small ion, small negative ion. Similarly, we will get a small positive ion. All these things will take place within about a microsecond. And later, these small ions will surround themselves with so many neutral atoms and molecules. They will become intermediate ions and large ion. These small ions have got higher velocity mobility in the atmosphere. They will lead to atmospheric electrical conductivity. This atmospheric electrical conductivity can be measured with a device called as Gaudian condenser. Gaudian condenser has got two cylinders. This is the schematic diagram of the Gaudian condenser. We'll consider one cylinder. A top one I am describing. This contains a cylinder marked with a red color. This cylinder we call as outer electrode. This is a cylindrical capacitor and this is the outer electrode. This blue line indicates the inner electrode. There are two electrodes in the cylindrical capacitor. Blue rod, it's a rod, solid rod. It is the inner electrode. This is the outer electrode. To the outer electrode, we can apply a potential, say 35 volts can be applied to outer electrode. The air is sucked between the two electrodes using a fan fixed at other end. Using this fan, air is sucked. That means air will move in this direction. That means between the two electrodes, air will pass through. This air contains small ions. It contains positive ions and also negative ions. Say for this cylinder, we have applied plus 35 volts. For the outer electrode, we have applied 35 volts to the outer electrodes. Therefore, all positive ions are repelled by this outer electrode and they are collected on the central electrode. All positive ions are collected on the central electrode. And all negative ions, they will be absorbed by the outer electrodes. By this way, this electrode will act as a sensors for the positive ions, and this the signal will be taken out from the central electrode and given to an electrometer that will measure the electrical conductivity of the atmosphere because of the positive ions. We call it as a positive electrical conductivity. Similarly, if we apply a negative potential to the another outer electrode of the second cylinder, then with this cylinder we can measure the negative conductivity. Most of the time, both positive conductivity and negative conductivity are equal because in the nature, in the environment, the positive number of positive ions and the number of negative ions is almost equal. But there will be a variations or changes in the amplitude of these quantities. We can measure these conductivity on the ground surface and also in the upper atmosphere using balloon-borne measurements. That will give rise to the conductivity, that is in the upper atmosphere. Conductivity is due to the cosmic rays also. In the ground surface, the conductivity is mainly due to the positive and negative ions created by radon and its progeny, whereas in the upper altitudes, it is because of the cosmic radiations. It will have its own interesting results. Now I am coming towards the only few interesting results. This pattern is called as the diurnal variations. Diurnal means variations throughout 24 hours in a day. That means the x-axis is time, varies from 0 to 4, 6, 8, 10, etc. ending at 22nd hour. That means at 10 o'clock. 12 o'clock is again 0th hour. This is the variation of ionization rate due to radon and its progeny. Radon is concentration measured with radon monitor. Progeny concentration is also measured with another radon monitor. And there, by using the concentration of radon and its progeny, total amount of energy released is calculated. From that, ionization rate is measured by thinking 32 electron volt is required to create 1 ion pair. This is the variation of temperature. This is the variation of relative humidity. This is the variation of wind speed, wind direction, and atmospheric pressure throughout a day. The concentration of radon can be measured close to ground surface using this type of techniques. This is the picture of balloon-borne measurements of conductivity. For the upper atmospheric studies, instead of using a bigger instrument like this, which I shown earlier, this is a bigger equipment. We can have a smaller one, which is shown here. For the bigger equipments, they are supplying electricity and also fixing a bigger fan, supplying the electricity for that fan and the electronic accessories. They are all complicated and it weighs up to larger mass. To reduce all these burdens, the small gradient condenser is developed and it is being used now. Now, this will reduce the both the manufacturing cost of gradient condenser and also the hydrogen gas which is required to fill the balloons. For these bigger balloons, we are using 7 cylinders of hydrogen gas, whereas in one cylinder I can fill 5 to 6 balloons for this small gradient condenser. That means we can use smaller balloons that will reduce drastically the amount of money required to carry out this research work. These are all electronic circuits, schematic diagrams. This is about so many equipments used in the atmospheric physics and also in the environmental radioactivity. I think I will stop now. And if there are any questions, please interact with me.
Sir, recently
How about 10-15 minutes stop time?
It was very nice, sir, to interact with you. You explained very nicely. So I have one question. So can you hear me?
Yes, sir. No, I am.
You have explained very nicely, sir, since from beginning and all. So recently we heard that near Manda somewhere some radiations are detected. Do you know about it, sir?
Not only in Mandya, at all places in our country, radioactive elements are there. Their concentration will vary from place to place. In Mysore region, Mysore-Bangalore region, Bangalore region contains highest concentration because of the granite rocks which are in that area. In Mysore also, only at selected places, higher concentration of these radioactive elements have been observed. In Gulbarga, near Gulbarga, at one place, they have identified the presence of uranium in the ground of Gulbarga. In some, they have identified a place near Gulbarga. The concentration is very high, and the government is also planning to mine uranium from that location. They have identified the presence of uranium by measuring radon concentration in borewell water. In Mandya district, also concentration is there. It's not very large.
Also in the basin of the river Ganga and Yamuna, also we heard some.
No, sir. No. Surface water does not contain radioactive elements. Sir, only groundwater, that is borewell water, contains radioactive elements. Okay. Surface water is by rain, and also if it is Ganga, it's from the Himalayan region. That contains a very small amount of radon concentration.
Okay, thank you, sir.
But in some states, in parts of Rajasthan and Punjab, very high levels of uranium has been observed.
Okay, thank you, sir.
Yeah.
Good afternoon, sir.
Please,
very nice presentation. I have one general question. So generally, this radiation occurs by what cause?
They are naturally present in the environment.
Environment means only uranium raw materials or some other materials?
Uranium, thorium, they are the primordial radioactive elements present in our Earth crust. They will undergo radioactive decay, producing series of radioactive elements. These radon, radium, they are all in the decay series of primordial radioactive element, uranium only.
Actually, in our state, Kudangulam, it's
Okay,
having
sir.
more
Yes.
raw materials for radiation.
Yes, sir, sure. Yes, I heard. Yes, I know that. The data also.
Naturally, it's having some raw material like this. It's having some more radioactivity. Yes, sir.
Yes, sir. More radioactivity is there. And for natural radioactive elements, we don't have any limits or control. It is naturally present from the billions of years. People are living in that environment. Therefore, we need not worry about the presence of radioactive elements in our natural environment. If it is there in the earth crust, nothing will happen. If someone purposefully mines those elements and in the surface, on the surface, if the concentration accumulates because of any reason, that may leads to health effects. That means if they do start mining process and the concentrated uranium, if it mixed with drinking water or in the natural air, then it causes serious problems. But if it is done by the government, they will take all necessary measures to control and monitor. We need not worry about it.
Okay, sir. Thank you, sir.
Sir, there is a possibility that the radiation taking place in rock. Have you measured so far, sir?
No, can you please repeat your question? I could not hear. Please hold the mic close to your mouth.
There is a possibility that the radiation taking place rock side, rock.
In rocks, concentration radiations are there. In granite rock particularly, the radon exhalation rate is more.
Oh.
And
so
also,
when it is removed,
we cannot remove. Remove.
So how much magnitude, sir?
It depends upon, sir. It depends upon the place, origin of the rocks. It varies from region to region. If we use those rocks as a construction material in our buildings, then indoor radon concentration will also increase. That is known and observed.
Is there any spiritual background, sir? Somebody told me that the radiation taking place only by the God, etc. Is there any possibility that the spiritual background is there?
No, I cannot understand your question.